Welcome back to my channel. In the last few classes related to switching theory and logic design, we have gone through Boolean algebra and minimization of switching functions using Boolean algebra. Based on that concept, we have covered some problems. Now in this class, we will understand the behavior of logic gates with the help of symbol output function. So there are few logic gates which forms the basis for any electronic device. So let me introduce what are the logic gates that we will cover in this class. So the basic logic gate is a NOT gate. It is sometimes also called as inverter. NOT gate can also be called as an inverter. Similarly, the second gate is AND gate, which is used to perform logic and operation between the input variables. Third gate is OR gate. This logic gate is used to perform logic or operation among the input variables. And the fourth gate is NAND gate. Fifth gate is NOR gate. Sixth gate is XOR gate, which is the acronym for exclusively OR gate or exclusive OR gate. Exclusive OR gate. And the last gate which we will cover here is exclusive NOR gate, means X NOR gate. X NOR. Exclusive NOR gate. Okay. So in this class, we will cover all these logic gates. Means we will see for each gate what is its symbol, which is used to, in logic diagram, what is its output function, and the truth table. If you have this basic knowledge about each and every gate, then only you can understand the design of any electronic circuit. So let me first go through the gate, which is first gate, which is NOT gate. Let me write here NOT gate. So NOT gate purpose is just to invert the input. Means the output of NOT gate is the form complemented form of input. Now, the symbol which is used to represent the NOT gate is this one. So usually we use this symbol to represent the buffer. Okay. Buffer, for buffer, whatever is the input that we are giving, we will get the same as the output. But for NOT gate, we need to invert the input. That's why we add a bubble here. Okay. So this is the symbol used to represent the NOT gate. NOT gate is a single input gate. So the input that I am applying, I am assuming it as A. The output of NOT gate I am assuming as Y. So as the output is the complemented form of input, Y can be written as A complement. So the complement is represented either by using bar above the variable or by using a dash above the variable. So these two are the representations which are used to represent the complement, right? In some textbooks you can also observe like that a complement, but these two are the most commonly used representations for complement operation. That's why I am using this. If A is the input variable, A complement is the output variable for a NOT gate. For example, if you consider x as the input variable, y becomes x complement. Okay. So this is the symbol of NOT gate. We call this as the logic symbol. So this is the symbol of NOT gate, and this is the output function of NOT gate. Output function of NOT gate. Now, how can you form its truth table? See, here we have only one input. That's why I consider only means one variable. So for one variable, how many possible values? For one variable, there are only two possible values. A can be either 0 or A can be either 1. If A is 1, what is Y? Y is A complement. That's why if A is 0, Y must be 1. If A is 1, Y must be 0. Okay. So this is a simple truth table. This is a simple truth table of NOT gate. Truth table always gives us what are the possibilities of input and their corresponding output. This is about the basic gate, which is the NOT gate. Next we will understand the symbol and output function as well as the truth table of AND gate. Let me show it. So I am taking a separate color to represent the AND gate. So the second gate is AND gate. Second gate is AND gate. So this gate is used to perform logical AND operation. AND gate performs logical AND operation among the inputs and provides the output. So let me draw AND gate symbol. So this is the AND gate symbol. Okay. So I am drawing a two input AND gate, which is most commonly used in practical electronic circuits. So the two inputs that I am considering are A and B. So these two are considered as the inputs which are applied to the AND gate, and the output is Y. Okay. So let me erase this small portion. So this is the exact symbol used to represent the AND gate. Okay. So this is the output of AND gate. These two are the inputs of AND gate. Now, as AND gate is used to perform logic AND operation among the inputs, the output can be written as Y is equal to A and B. Okay. So this is the output function. What we can call this as is, this is the output function, and this is the logic symbol for AND gate. Okay. Now based upon this output function, we can draw or we can frame the truth table. Okay. So you need to understand a lot of things. You can understand a lot of things from the truth table especially. So now if I want to draw the truth table, first I need to know what are the inputs. So these two are the inputs, right? So let me write like this. A and B are the inputs applied to the logic gate, and Y is the output of logic gate. So Y is equal to A and B, right? So this is the truth table, which gives us various input combinations that are possible and the output corresponding to that input, right? So now let me consider the input combinations that are possible. With two variables, I can have four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. So these are the four possible combinations of A and B, right? Now, what is the meaning for 0 0? At the input of AND gate, we are applying 0 here, 0 here. The meaning of 0 1 means I am applying 0 1 here. The meaning of 1 0 means here I am applying 1 and here I am applying 0. 1 1 means at A terminal we are applying 1, at B terminal we are applying 1 as the input. Okay. Now, according to logic and operation, if any one of the variable is having logic low, the AND operation always gives us logic low output. So here in first three combinations, if you observe, this is the first combination, second combination and third combination. In the first three input combinations, we can observe that at least one of the input is logic low, so that the output must be definitely logic low. So the output for the first three combinations is logic low, and for the last combination both inputs are high, so the output of AND gate is also high. Okay, so we can observe from this truth table, what we can observe is if any one of the input applied to the AND gate is 0, the output is 0. Okay, so I can consider like this. Let me draw the control input for AND gate. So this is the symbol for AND gate. Here you are having two inputs, right? Out of the two inputs, I am considering one input as the control input and another input, let me assume the another input as x. Okay, now y is equal to, how can I decide y value? Based upon this control input value. Okay, so control input can have two possibility. Is it right or not? As it is only one input, I can have two possibilities for control input. One is 0 and another one is 1, right? So if I want to get the input x to the output, if I want to get the input x to the output, let me assume, let me give a symbol for this control input as m. Okay, so if I want to send this input x to the output, it is decided based upon the control input. Okay, it is possible only by controlling this m. Now, how is it possible? For example, if m is 0, then whatever is the x value that we are applying here, it will not be transferred to the output, because if one input is 0, the output of AND gate is 0 irrespective of other input. If A is 0, for first two combinations if you observe, in place of A I considered the control input, in place of B I considered X. Now for the first two possibilities, A is 0, right? If A is 0, irrespective of B value, output is 0. See, for first two combinations, A is 0. When A is 0, irrespective of B value, the output is 0. Or else you can consider this first and third combinations. Okay, from first and third combinations, B is 0, B is common, and A values are changing from 0 to 1. If any one input is 0, irrespective of other input, the output is 0. So here also, if I make this control input as 0 only, if I make this control input as 0, then irrespective of x, y is 0. Now if I want to transfer the input from input terminal to output terminal, I can make this control input to 1 such that y can be written as, actually what is y? It is the output function of AND gate. What are the inputs that are applied to the AND gate here? M and X. So actual value for y is, let me write the actual value for y. It is M and X. This is the output function, right? Now when m is 0, the output will, the input, the whatever is the input that we are applying, it is not transferred here, and the output remains 0. So for m0, for m0, y is equal to 0 irrespective of x value, irrespective of x value. X can be either 0 or 1, irrespective of x value, y is 0. Hence we cannot so there is no transfer of input from the input terminal to output terminal. There is no transfer of input from the input terminal to output terminal. When m is equal to 1, for m is equal to 1, y is equal to x. So what is the meaning for that? For m is equal to 1, input, the input, if I am assuming this is the input signal that I am applying, the same input is transferred to the output. So for m is equal to 1, as y is equal to x, it acts like a buffer. It acts like a buffer, right? So this is about the basic thing related to AND gate and how we can control the input of AND gate. By considering any one of the input as the control input and making it to 0, you can stop transferring the input, or you can stop the flow of input from input terminal to input signal from input terminal to output terminal. When I consider m as 1 or that control input as 1, you can make this AND gate as buffer. Okay, this is possible with the two input AND gate. So this is about the AND gate and its logic symbol, truth table, and its basic behavior. Okay, now let me go to OR gate. Okay, so this is the third logic gate. So OR gate. So this OR gate, again, it is used to perform simply logical OR operation among the inputs. Logical OR operation among the inputs. Okay. So let me show the symbol for a two input OR gate. So I am considering this as an OR gate which has the two inputs A and B. So these two are the inputs, and the output of this OR gate I am assuming as y. So the output function y is equal to a plus b. Why it is a plus b? We have already seen the logical OR operation is represented by using the symbol plus, whereas the logical AND operation is represented by using the symbol dot. Okay. So you can represent the dot or you can eliminate the dot. There is no problem. But for logical OR operation, you must represent plus in between the variables, input variables. Okay. So this is the symbol for OR gate, logic symbol for OR gate, and this is the output function of OR gate. Now let me draw the truth table based upon this behavior of OR gate. So OR gate usually perform the logical OR operation among the input variables. Okay, you know what are the input variables and what are the output variables by now. So let me consider first the inputs. Then as it has only one output, I am calling it as output. So what are the inputs? Inputs are A and B. What are the outputs? Output is Y and it is related to input like this. So Y is equal to A plus B. Okay. So with the two inputs, how many possible combinations are there? 0, 0 is one possible combination. 0, 1 is another possible combination. 1, 0 is the third possible combination. 1, 1. These are the four possible combinations for the inputs, right? Now we need to understand what is the output corresponding to each input combination, right? So as I am performing logical OR operation, right, In logical OR operation, if any one of the input variable is logic high, the output is high. Okay. If you see the second, third, and fourth combinations, in these combinations, at least one of the input is high, so the output must be high. So the output is high for the second, third, and fourth combinations, whereas for the first combination, both inputs are low. That's why the output is also low. Okay. So this is the way of filling the truth table of logic OR gate. Okay. Now let me draw the control inputs for logic OR gate as we have studied, as we have understood the behavior of AND gate previously. Now we will see the behavior of OR gate. So these two are the inputs of OR gate. So in this way I can draw the OR gate. I am considering one input as the control input and another input as X. So this is the control input. So what happens if the control input is 0 and what happens if the control input is 1? Okay. So if the control input is 1 here, let me assume first, if the control input is 1, the output is 1. Okay. See the meaning, the thing behind this understanding is, when I am making this control input as 1, for example, the output is 1 irrespective of X value. Because for OR gate, if any one of the input is high, output is high. That's why I can write here, for M is equal to 1, Y is equal to 1, irrespective of X value, irrespective of X value, when M is equal to 1, output is equal to 1. So that there is no transfer of the input signal that is taking place here. Okay. Now for M is equal to 0, if M is equal to 0, what happens? We need to check for another input. In logic OR gate, if you observe the truth table, if any one of the input is logic 0, we need to check for another input to decide the output. If A is 0, consider A as control input. For time being, I am considering A as control input. So if A is 0, Y depends upon B value. Okay. So if B is 0, Y is 0. Similarly, again for the second combination also, A is 0, but B is 1. As B is 1, Y is also 1. So whatever is the input that we are applying, we are getting the same output if the control input is 0. That is the meaning. For example, instead of considering A as the control input, I am considering B as the control input. So for the first and the third combinations, if you observe, let me erase this one. So for the first and third combinations, if you observe, B is 0. So I am assuming now B as the control input. If B is the control input and it is considered as 0, whatever is the A value, you are getting same at the output. Whatever is the A value, you are getting same at the output. So what we can understand from this is, when the control input value is 0, Y value is same as X, because what is the basic logic function for Y, for OR gate? So Y is equal to M plus X. Okay. If M is 1, whatever is the X value, Y is also 1. If m is 0, y depends on x value. So y is equal to x value, x. When x is 0, y is 0. When x is 1, y is 1. So for m is equal to 0, y equal to x, hence it acts like a buffer. Okay. So this is the basic difference between this logic AND gate and logic OR gate. In logic AND gate, 0 is considered as the control input because when you want to stop the input to flow from the input terminal to output terminal, you can make this input to this control input to 0, so that this AND gate will be deactivated. So whatever is the input that you are applying, it is the output will not depend upon the input, and it give the same value as 0. Similarly, for OR gate, m is equal to 1 is considered as the control input. Okay. So this way you can understand the basic logic gates and their operation. So here the basic logic gates, in the sense we are considering logic NOT gate, we are considering AND gate as well as OR gate as the basic gates. Okay. In the next class we will see some more logic gates with their symbols, truth tables and everything. Thank you very much.